even though we always kind of just draw them as just CH3, or sometimes we don't even draw them at all, those methyl groups are taking up a lot of space on the top side of this molecule. And theory predicts that due to that steric interference of those bridging methyls, that the hydride actually prefers to come up from the bottom. Okay, that's what the theory predicts. So, in theory, if that endo attack is what we're saying is the favored approach for the hydride to take, we should be making the exo product here. And so that's what you're using NMR for. Right? We're going to take the NMR spectrum and we are going to determine which of those two is actually preferred. So I want to talk to you a minute about your NMR. So number one, when you go to take the NMR, you need a very concentrated sample. Right? If you don't have a very concentrated sample, you're going to get nothing but noise. All right, so try to concentrate the sample as much as you can. I'll talk to you about how to make a solid NMR sample next time, I think, because I don't think, most of you probably won't get to it today. But when you go to take your NMR, obviously not to scale. What you're going to see whenever you acquire your NMR spectrum is a mess. Especially in that 0 to 1.5 ppm range. It's just going to be a mess. Looking at the molecule, you can probably see why. Right? You have a whole bunch of protons that are very, very similar to one another. And so in that 0 to 1.5 ppm range, it's just going to be a mess of accidental equivalents. But that's okay, because you are going to completely disregard everything in this region. The only thing you care about are two peaks. That one and that one. And it turns out they have different chemical shifts slightly. So one of them is going to appear somewhere around 3.5, and it looks kind of like a triplet. And the other one is appears at around 4 ppm, and it looks kind of like a weird, misshapen doublet. That's the only thing you care about in the spectrum. So all you need to do, it takes a lot of work out of your NMR, so these NMRs usually go pretty quickly. The only thing you need to do is make sure your 0 is set, making sure your TMS is set to 0, and then just integrate these two peaks. Okay? Don't worry about integrating all the rest of the garbage 0 to 1.5. You're just integrating the peak at 3.5 and the peak at 4. Okay? So I'm going to just make up some numbers here to make my math easy. But let's say you did these integrations and you got 1.5 there and 0.5 there. You're going to use those relative integrals to get the relative amounts of each of the product. Okay? The way you're going to do that, let me call this one A and this one B. The way you're going to do that is you're going to calculate percent A just as a ratio of its integral, so 1.5, divided by the sum of the integrals. So it would be 1.5 plus 0.5 times 100. So that'll give you your percentage A, and then the B is calculated in the same way. The integral of B divided by the sum times 100 will give you the percentage B. Okay? Any questions on that?
Which peak correlates to the indole and the exole?
Honestly, I don't even remember. It's in the lab manual. Yeah. Okay. Any other questions on the NMR aspect of this, the integration part of this? Okay. Then a couple things about your reaction today. The borohydride reduction is very, very easy and very, very fast. I think you have to let it sit for maybe 5 minutes or so. So it's very quick. Basically what you're going to do is take a small Erlenmeyer flask. You'll put your sample in that. You're going to use methanol as solvent. And then you're going to come in and add the sodium borohydride. What you're going to notice is that as soon as you add the borohydride, it's probably going to start bubbling, kind of fizzing. What you're going to do once you add the borohydride is go ahead and gently heat that. Okay? So heat it gently on the hot plate, again, for about 5 minutes or so.
Like what
you don't,
setting?
What's that?
About what setting?
I don't know. I mean, the hot plates are all kind of different, so under 5 probably. Just you don't want to boil it. You just want to heat it gently.
Okay.
But the if you don't want it to run dry. So if you notice that some of your methanol is starting to evaporate and it's starting to get pretty low on the methanol, you can always add more solvent. Okay. So just make sure that you don't let it run dry. At the end of the 5 minutes or so, it's probably still going to be bubbling. What you're going to do is you're going to add cold water. What that should do is it should cause a precipitation to occur. So it should cause the borneol, isoborneol to precipitate out of solution. Okay. So I can't remember what the lab manual says. I think it says add 5 mils of cold water or something like that. That's an estimate, an approximation. You just want to add until you see precipitate. So if you add 5 mils, you don't see anything, then add more. Okay, so just add sufficient water to cause precipitation of the product. Once you see precipitation, place it in an ice bath for about 5 minutes or so, just get everything cold as possible. And then you're going to vacuum filter the product. Okay. Now remember, you're essentially filtering this out of water, so it's going to be fairly wet. So to kind of clean that up a little bit, or to dry it up a little bit, what you're going to do is scrape the product into an Erlenmeyer flask. Dissolve in dichloromethane. By the way, you did the filtration. Once you precipitated, you filtered it. If you have residue in that Erlenmeyer from doing the filtration, you can always add a little dichloromethane to that, rinse it, and then add here. So if you need to rinse that initial flask that you did the filtration from, you can rinse that flask with a little dichloromethane and add it to this Erlenmeyer flask. Okay. After that, dry over the anhydrous sodium sulfate. And finally, decant into something weighed. that point, it's kind of up to you. If you want to try to characterize, you could possibly go into the fume hood and evaporate your dichloromethane. If you want to just leave it till next time, you could also do that. Again, we have another full lab day on Wednesday dedicated to experiment 6, so there should be plenty of time for characterization of your 6B product if you want to do it then. Okay? This just depends on what you're feeling at the time. All right? Any questions on this?
How long should we leave the glass in the ice bath?
I don't know, 5 minutes or so.
So even after we get the cold water, you want us to put it in the ice bath?
Mm-hmm.
So why is that?
Oh, just to maximize the amount that comes out of solution. I mean, the ice water or the cold water should cause precipitation, but you know, the more it's not going to be. I mean, it'll be somewhat cold, but it's not going to be super cold. And so by putting in the ice bath for 5 minutes, it's just going to make sure that everything is ice cold. It just maximizes the amount of solid that'll come out of solution. All right. Any other questions on this? Okay, then you have what you need in terms of your starting material. I'm going to set the borohydride over by the balance.